Okay, so we're going to get started actually with chapter 1 in the textbook. And the title of this chapter is Preliminaries. And in this chapter, the objectives are, first we're going to start with giving a restatement of the two principles of mathematical induction. It's slightly different than the way we actually stated them in terms of sets. Here we're going to make them in terms of statements. Okay? Then we're going to look at a few applications of math induction to prove statements involving natural numbers. And these are going to be in the form of proving identities involving natural numbers or inequalities or other types of statements. Then we're going to look at some applications of the will-ordering principles to prove, again, some statements. Then we're going to introduce what is called the binomial coefficient. And then we're going to end with proving the binomial theorem. And we're going to see that the binomial theorem is a tool that we will be using in the proofs of other types of statements and theorems. All right, so let me get started by the restatement of the two principles of mathematical induction. The first principle, or we call it the weak principle, and then the second, or we call it sometimes the strong induction. All right, so first one is the following. So this is the first principle of math induction. In fact, most of the material in this chapter you should be familiar with, but we go in it just to have a good, an easy start. All right. So in here, remember the way we stated the mathematical induction, or the principle of mathematical induction, in terms of a set. That is a set of natural numbers which contains 1, and if it contains k, it contains the k plus 1. So if these two statements or these two conditions are true concerning or about a set of natural numbers, then this set of natural numbers is all the natural numbers. So in here we're going to do it slightly different. So we're going to let P of n be a statement such as some equality, some identity, some inequality, and so on. A statement involving a natural number n, a natural number n, such that first P of 1 is true. Mean the statement is true if it's an identity, in the two sides of the identity are equal to each other. All right. Or sometimes we say holds. Then the second one is if P of k holds, or is it true, for any fixed but, and let me say it actually, any unspecified but fixed, any unspecified but fixed natural number k number k, then P k plus 1 is true. All right. Now, if these two properties, two conditions are satisfied about a statement that involves a natural number n, then a conclusion, then P of n is true for all natural numbers. All right. When the principle of mathematical induction is stated this way, usually we refer to this one as we call this is the base step. The induction, and we refer to the second one as the inductive step. Inductive step. So when we assume that the statement is true for some fixed natural number k, which is going to be bigger than or equal to 1, then we can show it's true for k plus 1. One other variation we could have on this in this base step, sometimes, a certain statement holds not from 1 up, for the natural number. It might, does not hold for very fair, for the first few natural numbers. But it holds for, values from some point up. So we could replace this, and instead of saying P of 1, we might say that P of m, okay, this holds for some m, which is a natural number, okay? And as far as the inductive step is we can show that the P of k is true if then we can show that P of k plus 1 is true, then we have this. Now the conclusion in here, then we can say this is true for all natural numbers bigger than or equal to m. Okay, so we need that just a minor modification. All right, now the second principle of induction is actually stated pretty much similar to this, where again we're going to say, let's assume we have a P of n is a natural number or a statement involving natural numbers, then such that again, let me go back to the original statement that P of n actually is true, or this is true, but the second condition is slightly different. In here, we say that second condition that we need to be satisfied is f p of 1, p of 2, up to p of k. These are true for a fixed but arbitrary k. Bigger than or equal to 1, or in the second case, k is bigger than or equal to m, then p k plus 1 holds. Or so if this is the case, then P of n is true, or the statement is true for all the natural numbers. Or if we assume the the basis step start at m for the n through for all n bigger than or equal to n, being natural. All right, so let's look at the next objective is to prove some statements in the form of identities and inequalities that uses math induction. In fact, the math induction, one way you can use is to make a conjecture, I mean by experimentation, for certain values of n, and then this may suggest, a certain formula that you can make, and then you want to prove the formula. It's a true, actually holds for every natural number. Then you can use mathematical induction to actually do this. All right. So let's just start with the following example. Let us show that 2 to the 2n minus 1 is a multiple of the 3 for any natural number n. All right. Here's the proof. So we're going to denote that P of n be this statement. Sometimes after a while, actually, we don't need to be that formal. We could just actually say, well, I know what the statement I want to show, and I just show it for n equal 1 and do the math induction. Okay, so this is what I mean by when we have a statement. So this is just to kind of make this fit with the way we stated the math induction principle. So let this be the statement that 2 to the power 2n minus 1 is a multiple of 3. So this is actually the statement P1. Now let's look at P1. So this is the basic step. It's going to be that 2 to the 2 times 1 minus 1 is a multiple of 3. So let's see if this is true. Well, this number in here, when n is equal 1, so this is going to be 4 minus 1, and this is equal to 3, and yes, and the 3 is a multiple of 3, so it is a multiple of 3. So it means that here 1 actually is a true or whole. Second, the inductive step, we're going to assume that P of n is it true for, let me actually put P of k in here, just for some k unspecified, any is bigger than or equal to 1. So we know that this statement is actually true, right? We cannot say it is true for all, okay? So this is very important, is for some, all right? What does this mean? This means that we are saying that 2 to the power 2k minus 1 is a multiple of the 3. Of course, later we're going to rewrite this, what does really mathematically, how we can express this statement. But then we want to consider the statement for k plus 1. So let's look at what the statement looks like when n is k plus 1. So p of k plus 1, it means that 2 to the power 2k plus 1, replace that. And by this, minus 1 is a multiple of 3. So we're going to show this is true. Okay? So let's consider this number in here. And we know that we could write this one as 2 to the power 2k plus 2 minus 1. And I can rewrite this as 2 to the power 2k multiplied by 2 squared using properties of exponents. And this is equal to 4 multiplied by 2 to the k minus 1, like this. Now, the next thing we would like to do is we want to somehow come up with this 2 to the k minus 1 by itself, all right? And then we can use the, that this is as actually a multiple of 2. So we're going to do a trick in here. We're going to actually add the 4 and then subtract the 4. Now, the 4 I'm going to be adding in here, I'm going to be taking it with the first term in here, and then I'm going to be, actually let me take the negative 4. So let me take these together, group these together, and group these together. All right? So we can write this, and now 4 becomes a common factor. So we could write it 4 to the 2k minus 1. All right? And then the minus 1 plus 4, that's equal to 3. Now, so we're coming up with that expression that we know it's a multiple of 3. Now, since 2 to the power 2k minus 1 is a multiple of 3, this implies that 2 to the power 2k minus 1 is equal to 3 times q for some q being a natural number. All right, well, let's write this down. This means that this 2, that what we started with, we take this whole things out. So we can write, this is 4, and I can replace the 2 to the power 2k minus 1 by 3q, and then plus the 3. Now, as you can see, we can factor out the 3 out of this, and we come up with 4q plus 1, and this means that is the 2 to the power 2k plus 1 minus 1 is a multiple of 3. Which means that the statement that is, that is p of k plus 1 is true. So by the principle of mathematical induction, or simply by math induction, implies that the statement, okay, is it true for all n of course, we know what the statement is. It is 2 to the power 2n minus 1 is a multiple of 3. All right? Let's look at another example, and where we're going to show actually an inequality in this. All right? Let me look at another example. And prove that two to the power n is bigger than, strictly bigger than n for every n natural number. Alright, so this time I'm going to be a little less formal. So let's look at for n equal 1. The left-hand side is going to be 2 to the power 1. And this is bigger than the right-hand side, which is going to be equal to 1. So the statement means yes. So this is true. Next, we can assume that 2 to the power k bigger than k for some integer k or natural number k bigger than or equal to 1. And we're going to consider the statement or the inequality. Consider the 2k plus 1 like this. And once again, we could write this as 2 to the k times 2. All right? And this one is going to be because of 2 to the k is bigger than k, so the whole thing is going to be bigger than 2k times 2. So this is, this is by induction hypothesis. All right, that's what we call, assuming it's true for k. And that's what we call the induction hypothesis. Now, well, this means that this quantity is equal k plus k. And now we know that k is bigger than or equal to 1. So the best I can say in here, this is bigger than or equal to k plus 1, because I'm replacing the second k in here by a number that is actually smaller than that. Well, unfortunately, this is not going to be good for us because we're going to show strictly bigger than f. So one way to avoid, something like this is to actually do the statement for another integer, let's say 2. Okay? So for n equal to 2, when we have the statement also holds, means we're just doing it separately. So for this one, we have left-hand side is equal to 2 squared, which I know this is equal 4, and definitely this is bigger than 2, which is the right-hand side. So it means that the statement is true for n equal to 2. Now, in our inductive hypotheses, we can say that, assume that 2 to the power k is bigger than k for some k bigger than or equal to actually less than or equal to 2, okay, no, it's actually bigger than or equal to 2 as well, all right? Or in this case, we could assume it's true for k1, and actually we could go with bigger than or equal to 1, okay? In particular, it's true for 2. But now, in here, we, instead of saying this is bigger than, we could put actually strictly bigger than actually 2. And in here, of course, k is bigger than or equal to 2. All right? Actually, in here, I better put in for some k bigger than or equal to 2. Because already we proved it for 1 and 2. So let me actually do this. All right, and so what we have shown in here that then 2 to the k plus 1 is strictly bigger than k plus 1. This holds. And by math induction principle, the statement is true for all. So this is true for all n bigger than or equal to n. All right? We'll look at one more example using the first principle of math induction, and I want to look at another example using the second principle of induction. So here's another example. I want to show that if you take this identity, or to prove this identity, so this is the sum of the reciprocals of the product of two consecutive natural numbers up to n plus 1. So this is equal to n plus 1. This is a very nice formula, because instead of adding all of these, it says that you could actually get the same thing by just plugging in those numbers you're adding, okay, the reciprocals in here. All right, again, for n equal 1, as you see the last term in here, this is going to be 1 by 2 for n equal to 1. So we only have actually one term in here. So this is 1 over 1 times 2. And this is the left-hand side. All right, so this is left-hand side. And the right-hand side, when n equal to 1, is going to be 1 over 1 plus 1. And this is 1 half. So these are actually equal to each other, right? All right, let's assume that statement is true, or the identity hold for some k bigger than or equal to 1. And this is equivalent to saying that we know that this is true. Then k plus 1. Some people sometimes use even the same n, okay, instead of using another letter, which is fine. And then this one is k over k plus 1. So we can assume that this is true. Then we need to show that the statement is true, or the identity is true for k plus 1. Okay? So let's see what does it look like for k plus 1. So the identity for the, I don't want to say the identity, I want to say just for k plus 1, left-hand side becomes this. So we're going to have actually all the terms in here for k, and we have the extra term that we add. That is going to be k plus 1, k plus 2. All right? So this is what the left-hand side looks like. Now, by induction hypotheses, we know this is equal by induction hypotheses. We have this equality which says that this is going to be k over k plus 1 plus that extra term. Now, let's add up these two fractions, and hopefully it will simplify to what we need. So this is going to have a common denominator, k plus 1, k plus 2. So this, we need to multiply it by k plus 2. And this one, we don't need to adjust it. And now we multiply, we get k squared plus 2k plus 1 over k plus 1, k plus 2. Now if I factor out the numerator, come up with k plus 1 and k plus 1. That's just the k plus 1 squared. And then we have k plus 1, k plus 2. Upon canceling out a k plus 1, we end up with what the identity should be. All right, so this is the right-hand side for k plus 1. And now, the principle of mathematical induction inform us that the statement or the identity holds for all natural numbers. All right, let's look at an example that involves applying the second principle of induction. We're going to see the necessity for it. Even though logically the first principle of induction is equivalent to the second. Means if we assume one, we can prove the other. Both of them are equivalent to each other. But in the proofs, such as the following statement, it would make life easier to actually just do it through the second principle of induction. All right? And here it is. So this is what I want to show. Prove that every natural number n bigger than or equal to 2 is either a prime number or is a product of primes. Two or more primes, basically. Okay? So this is the statement that we need to show, to prove. Okay? So in here we want to start with 2 for n equal to. The statement is true. Is true since 2 is a prime. All right, now let's assume that the statement is true for 2, 3, 4, up to k, or some k bigger than or equal to 2. Now, next we're going to consider k plus 1. Then, by the definition of a prime and composite, either a number is a prime or is not a prime. Remember that we are not including 1. 1 is by itself, actually. Consider this. Then, either k plus 1 is a prime, or k plus 1 is composite, or not a prime. Well, if k plus 1 is a prime, statement is true. The statement is true. And we're done with this, all right? However, if k plus 1 is composite, then we need to apply what does that mean. On the other hand, if k plus 1 is composite, by definition of composite, this implies there exist R and S, okay? These are natural numbers such that R bigger than or equal to 2, less than actually the k plus 1, and 2 less than or equal to S less than k plus 1. And of course, the k plus 1 is the product of R and S. Now, important step. Now, since R and S are less than or equal to k, by induction hypotheses, either one of these is a prime or a product of the primes. Then either R or and S are primes or product over primes. Hence, when we put all this together, k plus 1 is a product of primes. It cannot be a prime, of course, even both of these or one of them is a prime, because we already have a prime. Then by that induction principle, by the principle of math induction, the statement holds for all n bigger than or equal to 2. All right. let's look at some applications of actually the will ordering principle. All right. Let me start with reminding you or stating the will ordering principles. So look at applications of will ordering principle. Remember, the will ordering principle states that we have S be a non-empty set of integers or of natural numbers. Then S has the least or smallest element in S. So that is the element actually does belong to S and it is smaller than or equal to all the elements in S. All right, the first application I want to look at is called Archimedean property for the natural numbers. So here is actually theorem 1 of the book, and this is on page 2. And state the following: if A, B are natural numbers, then there exists n, a natural number n and n, such that NA is bigger than or equal to B. Actually, this statement is actually holds for any real numbers, okay? This statement holds if A, B are real numbers and B bigger than and actually A is bigger than 0, means positive, then again there exists a natural number such that A(n) is bigger than or equal, actually strictly bigger than B. All right. So this property, either for natural numbers or for real numbers, is called Archimedean. Archimedean property or principle. Its proof for the natural number actually require the use of what is called completeness axiom. All right. So of course we're going to only show it for the natural number because these are the type of numbers actually we are interested in. But it's nice to know if actually it holds for other types of numbers. If it holds for the real numbers, means it holds for the rational numbers, and so on. All right. The idea here is, as we have in here, we're going to be applying the will ordering principle is to create a non-empty actually set that we can say that of natural numbers, so that it would actually require that it has a least element. The proof is actually by contradiction. We're going to do it here. Proof by contradiction. Now, it's very important to state what does this mean. So we're going to assume that for some, because this is for all, when you do contradiction, you want to say for some A, B natural number, and for all n, in n, we need this statement to be incorrect, which means n A is strictly less than B. All right? Now, this statement or this inequality is equivalent to saying that 0 B minus NA. So this is true, or this one for every n in n. Now I want to create a set that I can of natural numbers or positive integers, and this set is going to consist of numbers of this form. So we're going to define S to be the numbers of this form. So B minus NA, all right, such that, let me put this is in N. Well, actually I need to see if it is in N, okay, but it's very clear, okay, so this is N in N. Definitely this is a subset of natural numbers, provided that this one is bigger than actually 0, all right? Bigger than or equal to 0. But in here, we know that since B minus NA is bigger than 0 for every n in n, yes, this becomes actually a subset of the natural numbers. All right? All right. Now we need to see that this is not empty. Okay? S is not empty since B actually belongs to the set. In this case, then B is equal B minus actually 0 times A. Well, in this case, we're going to be assuming that the natural number, so we actually put in maybe a 1 in here. So let me say actually B minus A is to be in the safe. So this one is actually an S, where the B minus A equals B minus 1 times A. Let's strictly write it in this form. So we have an unempty set of natural number by the will ordering principle. Implies that there exists an element in here, there exists S in S, such that S is smaller than or equal to every element B minus NA, all right? And for every n being a natural number, okay? Now, this S is going to have, since S belongs to S, this implies S is going to be of the form A minus M times B for some, M being a natural number. All right. Remember that we're going to find a contradiction because we have something. And let's see what happens when we look at this. All right? So we have actually this S is equal to A minus, sorry, we're going to define another number. Let y equal A minus M plus 1B. Now, I know this is in S, okay, because it does have the form of the elements of S, is A minus a multiple, natural multiple of B. All right, let's look what this is equal to. This is equal to A minus MB minus B. And this is equal, now the A minus MB, this is equal S minus B. And since B is a natural number, and this is S minus B, is actually less than S. All right, since B, if you wish, is bigger than or equal to 1. So we are subtracting out from S a number that is actually positive, all right? Well, but this contradicts that S is the smallest, all right, natural number, or the smallest number in S. So this S minus B is a natural number, and we have the this S minus B is going to be smaller than S. This is a contradiction, since actually this one is, we put it in this way. This one is going to be, this is an element actually in, actually the Y, I want to say the Y. Y is in S, and Y actually is smaller, so this one is a contradiction, since S is the least element in S. So we found a smaller element in S that is smaller than S. All right. Let's look at another example. And this example is interesting. I hope you find it interesting. Where we're going to use the will ordering principle to show that the square root of 2 is a rational number. Here's the theorem. And this theorem, or this proof, is given by, actually let me put the proof, this one is known for a long time. The number that's the square root of 2 is irrational. Probably you've seen this one in many classes, many courses you've taken as an undergraduate or as a graduate student. In here, I want to present a proof that is different, okay? And I'll kind of go over the proof, the traditional proof given to this statement that the number 2 is, square root of 2 is irrational. However, this proof is due to Steinheim, Ogo, Stein, Haas. It's a Polish mathematician, the traditional way to prove this, because this is on the side in here, is by contradiction. So you assume that this is equal A over B, where there is no common divisor between A and B. These are natural numbers. And then you square both sides of this equation. And then you multiply. And this statement implies that A squared is an even number, has a factor of 2. Then you need to say, or from here you conclude that A itself is going to be even. This needs a proof, of course. And then once you do this, you're going to find a contradiction because you're going to find the A and the B that you started with actually have 2 as a common factor, okay? Which, contradict that from the very beginning you assume that they don't have any common factor. All right, so this is the way it is done in many, many places. So in here we're going to do it in a slightly different way. Again, we're going to be using contradiction. So we're going to assume that a square root of 2 is actually rational, means equal A over B for some A, B being natural numbers. Everything is positive here, so natural. However, we're going to go in a different direction from here on. We're going to define a set of natural numbers like this. This set I want to call E. So this consists of actually integers or natural numbers S and N such that there exist R and N such that square root of 2 is equal to R over S. Well, we explain, how this set is defined, it's well defined, and so on. So this is a set of natural numbers, and what I'm saying is this set is defined such that there exists an R and N, and where the square root of 2 is equal R over S. Whenever you define a set, you can do kind of whatever you like as far as it's not empty. Means that's one thing you want to have of consider. All right. Now I claim that this is a set of natural numbers. Whether this stuff I have in here, the defining property, actually makes sense or not, that means if this set has something in it, it's not empty. And I want to show you that it is. Okay? So the claim here is E is not empty. Let me practically put it more in here. E is a non-empty set of natural numbers. Being a set of natural numbers, that's exactly what we're saying in here. S is actually an M. Now, what is left is to show it is not empty, basically. Now, by our assumption, by our assumption, B is actually in E, since square root of 2, there exists the a that we have assumed in here, where when you take this a with that b, it gives you the square root of 2. All right? So now we have a non-empty set of natural numbers, and now we need to apply the Will ordering principle. Okay? So by the Will ordering principle, E has a smallest element. Let's call it little e, and this is equal m over n for sum m, n, and natural. All right, so what we have in here, this e actually is going to be the square root of 2. So this means, this implies that m over, I'm sorry, this is this language, this is not consistent. Okay, so I want to call it m. Sorry. Let's call it m. Okay, so m is in E. This implies there exists, so this implies there exists an n in n such that the square root of 2 is equal m over n. Or, yeah, the elements of E are natural numbers. Yes, we take ratios, but they are the defining condition. Okay, so it's not the elements. All right, let's move on. Now I'm going to take this, I'm going to square both sides. So this becomes, the left side is 2, we have m squared over n squared. And for me, I'm going to do basic algebra, basically. I'm going to cross multiply. So this gives me 2n squared equal m squared. And then I'm going to subtract from this mn, subtract mn from both sides. So we get 2n squared minus mn equal m squared minus mn. I want to factor an n out of this. So this becomes 2n minus m, and this becomes factoring in m. And then I'm going to be dividing this one out to get actually m over n is equal, rearrange it basically, is equal to this. Now, this makes sense provided that the denominator does not equal to 0. Okay, so this is provided, this is legitimate provided m minus n does not equal to 0. Well, it must not equal to 0. Okay? So yes, m minus n does not equal to 0, because otherwise m is going to equal n, and this implies m over n is equal 1, and definitely this is not the square root of 2. Okay, so we cannot have that equal to 0, so it must not equal to 0. All right, let's see what we have in here. Okay, we put it up there. So we have from these computations, we have square root of 2 is equal m over n, and this is equal also to 2n minus m over m minus n. All right? Now I claim, actually there's one other thing I want to bring in here. Yeah, so actually I claim that the m minus n is smaller than n. All right? So this is the denominator in the first fraction, which gives us the square root of 2, and this is the second. All right? And I know this, again, is going to be a natural number in here. All right? All right, so this is what we're going to do for this claim. And once we do this one, means we produced a natural number that is smaller than the, actually the smallest, right? Let me see in here. What is my, okay. I am sorry. Let me go back and make one correction, okay? In the statement I made about the principle of with ordering principle, we're going to say that E has a smallest element. We're going to call it N. I'm sorry, I saw this one I wrote is actually M, okay? So M is incorrect. N. I want to show the N. Everything else is true, but actually the denominator I want to be the smallest. All right? So I'm going to show that the M minus N is going to be actually smaller than N. To do that, we're going to start with a very simple inequality. I know that 2 is between 1 and 3, but I want it between 1 and 4, okay? Then we're going to take the square root of this inequality. Since everything is positive, it is not hard to show that when you take a square root, it preserves the the inequality. So we get this. And this is equal to 2. So this means that the square root of 2 is between 1 and 2, okay? So we have 1 then the square root of 2 less than 2. Now let me put this in here actually as m over n, like that. And again, I want to multiply throughout by n, because it's positive again, so multiply by n. So we get n less than m less than 2n. And then I'm going to subtract n. So we get here 0 less than m minus n less than n. So we have shown two things actually. That the n minus m is actually a natural number because this is bigger, and also this is less than. So okay, so we have a. So this means that the claim holds. So the claim holds. So it's true. But this contradicts that n is the smallest. Remember that this one right here, this is also the one actually I wanted to say. This is actually a natural number, all right? So So this one, that n is the smallest element in A. All right. Well, something went wrong then. The well ordering principle, we know it's a true statement. It does hold, but we ended up with something to contradict that. And the problem is our assumption that E is not empty. So E not empty is not the truth. So what does this mean? This means that the way we define or made actually E to be not empty by assuming that the square root of 2, all right, is actually equal this A over B from the very beginning. All right, and this proves that the square root of 2 is not a rational number, or it is an irrational number. All right, few things left in here, and that is introducing the binomial theorem. And to do that, we need to consider an important symbol or concept that is of binomial coefficients. Okay, so we're going to define the binomial coefficient. So in let n, k to be natural numbers such that k is smaller than or equal to n. The binomial coefficient is, actually it's going to be a natural number, is denoted by this symbol, n in the top, n over k, between parentheses like this, and is defined by this formula. Okay? So n k is equal n factorial, then k factorial, then the difference between these factorial. Now I want to make this as actually a fact. A fact means something I'm going to state without a proof. That n k is actually a non-zero or non-positive, means this one belongs to the set of integers, positive integers. No, actually, sorry. This belongs to n. I'll use this one, union 0. All right? I want to also define this when k is actually bigger than this. Moreover, if k is strictly bigger than n, we define, kind of we force this, okay? We define nk to equal 0. So with this way, then we have, this is defined basically for all natural numbers. Of course, this is not going to do any good, but at least this is something we can have. All right. Of course, to show that this is actually a natural number, this is, as you can see, because it looks like there is a fraction in here. But somehow, with a lot of these terms actually cancel out, and we're going to see it does actually produce a natural number. All right? So let's look at the front form. We could write this in so it's not very hard to show that we can have this written in different ways. So initially we have this is n factorial, then k factorial, and n minus k factorial. If I expand the n factorial, means write it as this product, 1 times 2 times 3, and so on, up to, this is n minus k, then the next one is going to be one bigger than this, n minus k plus 1, and so on, up to we reach n minus 1 and then n. All right? So start with 1 and so on, and then we keep adding all of this. And then the k factorial here, I'm going to leave it as k factorial. And then we have this n minus k factorial. This one is 1 times 2 times 3 and so on, up to n minus k. All right. Now we can cancel out all of this with all of this. And we have a different form, different way of writing the this. I could start with n minus 1 up to n minus k plus 1 over k factorial. I don't know if you want to memorize this, you don't need to, you can derive it, that's what it is. However, there are the following lemma, which actually easy to show. So here again, we're going to let n, k be natural numbers. Then, actually even k we allow it to be equal to 0, so maybe I should say this is together with 0. All right? Again, such that we want to say that actually the k is less than or equal to. So I'm going to have this one under this assumption. Then, first one is if you take n0 is going to equal nn is going to equal 1. Okay? So when k is equal either 0 or 1, this is equal to 1. Second property is more important. Nk is equal nn minus k. So this gives you some sort of symmetry among the binomial coefficients. So, and you can see this from the next result that we're going to prove, which is called the binomial theorem, that the coefficients with the different powers of the binomial, the two terms that we are squaring or cubing and so on, they are actually appear symmetrical. Okay? In the beginning, if you put in a reflection on the middle term, you're going to see they are the same. All right? The proof of the first two is very, very straightforward. And actually, the proof of the second is also not very hard. So I'm just going to leave the first two for you. So the second is the. So let's look at nk. Well, this is equal by definition, again, n factorial, k factorial, then n written here. I'm going to write this as n factorial, k factorial. I'm going to add and subtract n from the n minus k. So I'm going to add an n, subtract an n. Because nothing changes. Then I want to rearrange this and write it as n factorial, k factorial. And then I want to take this as actually n, let me see here. Let me take it as n minus k. So in other words, I am, so when I distribute this, let me see here. Okay, I think I need to, actually, I didn't done it our way now. Let me correct myself. So I want to change the k factorial into n minus n plus n. Sorry. And this I want to leave it as is. All right. So let's see what this is equal to. N factorial. And I can write this one as n. And then we can say this is n minus. Let me see in here. What the heck I'm doing in here. So this is let me see this one. Yeah, I want to write this one as n minus k. Sorry. Factorial, then n minus k factorial. Let me rearrange this. This is n factorial. And remember that what's inside here, this is actually equal to k, all right? But, and this one is n minus k factorial. So if I rename, all right, this, if I call it m, and this is m, so this becomes n factorial over m factorial, then n minus m factorial, and this together, it's equal n over the m, right, which is just n minus k. All right, and this is equal, of course, the right-hand side. So this is the left-hand side, right-hand side, they are the same. All right. Let's look at just an example of manipulating this binomial coefficient, okay? So I look at one of the problems in the this section and go over that. Okay, so here's an example. This is actually problem number 8 on page 12. Okay, where we're going to show that for all n in n, the binomial coefficient of 2n n is equal to this expression. Okay, 1, 3, 5. This is the product of the odd numbers from 1 to 2n minus 1. And then here's 2, 4, 6 up to 2n, and this is 2 to the power 2n. All right, let's go and prove this. at the left-hand side, so this is going to be 2n factorial over n factorial, then the difference between these, which is n factorial. Now, remember 2n factorial, it doesn't mean it is 2 factorial times n factorial. Actually, this is not true. It means this is, by definition, is the product of 1, 2, 3, up to 2n. And in the denominator, we have, of course, n factorial quantity squared. All right? All right. So let's go to the numerator. I want to write it in, separate the factors that are even and the ones which are odd. Okay? So let's go with this one. 1 times 3 times 5 up to the number before this, which is going to be 2n minus 1, right? So we have this. And then I want to take the even numbers, which is going to start with 2, then 4, then 6, up to 2n. All right? And the denominator is going to be n factorial squared. All right. The second factor, it has each of its terms, each of its subfactors has a 2 in it. Okay? Let me take this one out. So in here, each one of these has a 2. So I want to factor a 2 out of this. So 2 times 1, this one is 2 times 2, this one is 2 times 3, and this one is 2 times n. And then I can say that equal to, put the whole thing in here, we have 1 times 3 times 5 up to 2n minus 1. Then I want to take a 2 out of this. How many 2's are in here? Well, there are actually n of them. So we have, if I remove all of these, so we're going to have 2 to the n, and we're going to be left with 1, which comes from the 2, and then 2 from the 4, and then the 6 is going to have a 3, and so on, and the 2n is n. And then we have the n factorial squared. Now, this product in here is going to be n factorial. So this cancels out with the square in here, and we end up with exactly what the right-hand side, where it's only one n factorial, and then we have 2 to the n, and this is right-hand side. So a lot of these questions in this chapter and the binomials, which basically, this is why you do, you just manipulate using the binomial coefficient. All right, now we need to prepare for proving the binomial theorem. And to do that, I need another limit or another result is called Pascal's identity. Actually, this is the basis for Pascal triangle. For Pascal triangle. So we're going to look at how the relationship between actually these two. So let's say the following. Again, let n, k be natural numbers with k less than or equal to n. sum of the binomial coefficients nk and k minus 1 give you the same as n plus 1 k. Okay, so this is the sum of two binomial coefficients. You can combine them into one binomial coefficient, and you see the differences on the n and the k. All right, so you could use it either way. The proof is very, very simple in here. Is again, the idea is to take the left-hand side. Looks like there's something you can do with it. And this is equal to n factorial over k factorial, n minus k factorial, plus n factorial, k minus 1 factorial, and n minus k plus 1. We subtract, so it becomes like this factorial. Well, we need a common denominator on these. So as you see, this one needs a, actually, this is here. Yeah, so we need to multiply this by an n. One other thing in here, because we could write this one, as you see, we could write this as k, then k minus 1 factorial, so we don't need this. So I need to have this common denominator. So I want to multiply this is by this, and I want to multiply this is by k. So I want to multiply up and down by this is n minus k plus 1, that fraction, and this one I want to multiply it by k. So multiply this is by k. Well, we're going to see that with this done, that we do have, so that's equal to, we look at the first n minus k plus 1, and I want to be writing this as k, then we have n minus, k minus 1 factorial. Or actually, no, sorry, let me leave this as is. It's going to be k factorial, this n minus, these together, I can put them together and it gives me actually n minus k plus 1 factorial. Okay, so this is n minus k plus 1 factorial. And the other one is going to be n factorial times k, but the n minus k factorial together with the k give me k factorial. And then n minus k plus 1 factorial. So yes, we can have actually one fraction in here with a common denominator of k factorial, then n minus k plus 1 factorial. And then we have this n factorial. Let me also factor it out. So we get n minus k plus 1 plus k. So all together, we have n factorial times n plus 1. The k's cancel out, have this. And the denominator, of course, as is, plus 1. All right? Well, let's see, write that one as a binomial coefficient. Well, we need one more step. So we could write this one as n plus 1 factorial, then k factorial. Then I'm going to write this one as n plus 1 minus k. All right, again, if you go, this is m. So if this is m minus k, and you're going to see that it's equal to n plus 1 and k, and this is the right-hand side. All right? Now let's make the connection between this and Pascal triangle. I am sure that you are familiar with Pascal triangle, where let me put that one, let us start with 1, then you have 1, 1, then you have 1, and then you add these 2, and 1, then so this is n equals 0, this is the row 0, this is n equal 1, this is n equal 2, and n equal 3. We start with 1, then the 3, which we add these 2, and then we add this one and this one. This gives me 3, and then 1 on the outside. And this thing continues. And this one is the coefficient when we take a plus b to the 0, which we know that is equal actually to 1. So that's not very exciting thing in here. This one, it gives us the coefficients when we have this. This is going to be 1 times a basically, and 1 times b. All right? And this one, when you have the a plus b squared, so this is equal to 1 times a plus 2 times ab plus 1 times b. So these are give us the coefficients, okay, the numbers in front of the different powers of the the a and the b in here, and similarly in here. So it turns out that actually the k plus 1 entry in, and actually this is where, let's see in here. So this is the way we find the sum of these two is equal to this, and the sum of these two is equal to this. And this is what the Pascal, all right, I didn't say. This one is n equal to 2. Okay, so you go to 2, and you want actually to add 2, and this is the first, plus 2, the second. This is equal to the third row, and then we have the this one in here is going to be actually the k minus 1, and that one. Let me see the. Shall I go back in here? So we have k. So this is k. Actually, this is k. Sorry, this is k. This is k minus 1. And what's God is saying that when we take this, where the this must be equal to 2, right? And this is exactly what this is 3 is. And this is true all the time, all right? This is true for all others. All right. The last result that we proof we're going to do in here is the binomial theorem. And here's the this formula. It's actually theorem or formula, sometimes we call, or formula. And give us the expansion of, or the expressing of the sum of two. Now, but actually, these could be actually even real numbers. Doesn't have to be just integers. To n, where n is a natural number. So the theorem says that you go with n, 0, then a, Let me go with the n in here, then b to the 0 plus n1. The a exponent is going to be reduced by 1, and the b is going to increase. And this thing continues with a n minus 2 b squared to the last one where things flip. So this is n, so, and then the a becomes to the 0 and the b to the n. All right. A nice way to express this is using summation notation. So start k equals 0 to n, and then the binomial coefficients, and then we have a to the n minus k, then b to the k. So this is called the binomial formula or theorem. So we're going to do this, the proof is by induction on n. Sometimes we refer whenever we have, different numbers in here, and we refer to what we are doing the induction on by saying the induction on which natural number. So for n equal 1, the left-hand side is equal a plus b to the 1, which is a plus b. Let's look at the right-hand side, which is supposed to be, we're going to use the summation. Okay, so k equals 0 to 1, then 1k, then a, 1 minus k, and b to the k. Well, let's run the summation. So we're going to start with k equals 0, plugging in side the summation. So this one is 1, 0. Then we have a to 1 minus 0, b to the 0, plus, when k equal 1, and this is the last value for k, and then this is a, 1 minus 1, b to the 1. And once you simplify this, this is going to equal 1, 0. Remember that n0 is equal to 1, so this becomes a, and b to the 0 is 1, and then we get in here again 1, 1 is again 1, you get 2. So yes, so the two sides are equal to each other, and the statement for the formula does hold. Next, we're going to assume that this is true for a k, or for n. Let me actually use n because we're using the k for a different purpose. Okay, so we're going to assume that the formula holds for n bigger than or equal to 1. Some n. We put here for some, not for all. All right? So this means this is equivalent to saying that a plus b to the n, this is equal, k equal 0 to n, and k, n minus k, ek. Now remember this one we are saying for some, it's not for all. That's our purpose is to show for all. So we're going to consider then the expansion of a plus b to the n plus 1. Well, we know that this is equal to a plus b to the n times a plus b. So I can separate these. Then I'm going to distribute this inside the parentheses. So this gives me an a plus b to the n times a plus a plus b to the n times b. I'm going to take each one of these terms and work it out. basically using the induction hypothesis, and then we're going to kind of combine them back together. So let's look at this term. A plus B to the power n times A. Well, this is going to be equaling to A multiplied, because of the statement is true, so I can use the K equal 0 up to n, nk, then A n minus K times B to the K. Then I can pass the A inside the summation. Really, what I'm doing, I'm distributing, because this is a sum of n plus 1 term. I'm distributing it for every term. So each one of them is gonna, the A of it is gonna change. So this goes to equal 0 to n. nk, the coefficients, it's not gonna be affected by multiplying by A. But now the exponent of A becomes n plus 1 minus K, and the B does have nothing to do with the N. All right, so this is, we have this. We're gonna actually come back to this, or let me see, but then I don't have to beat myself in it. Yeah, actually, let me simplify this by taking, for K equals 0, I want to take it up, sort of. So when K is equal to 0, we have n 0, that's equal to 1. Okay, let me actually put it in here. So this is n 0, and then we have A n plus 1 minus 0, then B to the 0, and then I'm going to continue from K equal 1 to n by the summation. And then this one is not going to change. Let me go up here. Okay, so let me. So let me go from here. Okay, so we're going to go all the way. So this is equal. So I want to pull out for K equals 0. So K equals 0, I want to have it in here. So it becomes n0. So this is K equals 0. All right, so this is this, and then the A comes n plus 1 minus 0, and B to the 0. And then all other terms, it's going to start from 1 to n. I will have the summation for this. So nothing changes. Now, this one give me 1 and the B to the 0, so all of this is going to give me A to the power n plus 1. Okay, so this is all of this is A n plus 1 plus that. Okay, let's do the second one, which is the A plus B to the n times B. Okay, so let's write that down. So remember, this one is the A times A plus B to the n. All right, which is the same as that one. Yeah, just like it. Then we have B times A plus B to the n. So this is going to be B, and this is K equals 0 to n, in K, A, n minus K, then B to the K. We're going to do something similar to what we've done for the first term, this one. And this time I want to pull out actually the when K is equal to n. Okay, so when K is equal to n, so this is starting from, let me pass this inside, I'm sorry. So let me first multiply. So So this becomes k still equals 0 to n k. The a is not going to be changed, but the b becomes k plus 1. All right? So I want to take the last term, okay, for k equal n, okay? So I want to bring it in the front. So this becomes n, then a, n minus n, then b, n plus 1, and then the summation is going to start k equals 0 to n minus 1. And then we have these terms doesn't change. N minus k, then b, k plus 1. Well, when I simplify this, the n is going to be giving me 1. The a to the n minus n is equal to 1. So we end up with just b to the n plus 1. Well, fortunately, I cannot combine. I would like to combine this, especially this summation with this summation, because they don't start and end at the same entity. So we need to make actually we call shifting the index, all right? Or making a change in the index. So if I start, this is from 1, let me write this one in here, n plus 1. I want to start from k equal 1, all right? And I would like that k equal 1 to give me the same value if I plug in 0 in here. Well, if you put here k minus 1, so when k is equal to 1, this gives you 0, and then you need to make changes for also the k's in here. So you're going to replace them by k minus 1. So this becomes a to the power n minus k minus 1, like this. And then the b becomes k minus 1 plus 1. All right? Turns out that we get, and then this n minus 1 actually goes to n. Because here we started, instead of from 0 to n minus 1, we start from 1, then we expect to have the same number of terms to add up. All right, now if I simplify this last thing in here, let me write it down. So I'm just going to take all of this out and just bring in this last thing. So we have b to the power n plus 1, and the summation goes k equal 1 to n, and this is nice, n k minus 1, and the a becomes n minus k plus 1, or plus k plus 1 rather, minus k, let me write it this way, and the b to the k. We're almost there. All we have to do is now to add these two. So we're going to add both sides. So this side becomes a plus b to the n, plus b, a plus b to the n. And this is equal, there is a plus sign here, so we need a plus sign. So this becomes a to the power n plus 1 plus b to the power n plus 1, like this. And then the summation plus k equal 1 to n. And then we have n k plus, remember that this and this are the same. So these are the same. So when I want to add, I just want to factor them out. So this is a n plus 1 minus k, and this is b to the k. Well, and in here we need the binomial coefficient becomes n k minus 1. Now we need to use Pascal identity to replace this with n plus 1 k, and in the a to the n plus 1 minus k b to the k. We have summation, but this summation starts from 1 to n. And but we have these two terms too. We would like to absorb this term inside the summation. And it turns out that if you evaluate this summation at k equal to 0, and you put 0 for k, this gives us actually the an plus 1. And if you go to n plus 1, it gives us, put n plus 1 in here, it gives us the b to the power k. So what does this mean? This means that if you change your summation, instead of going from 1, go from 0, and go all the way to n plus 1, then we get this formula, or this summation. And this summation, this is the formula for n plus 1. Formula for n plus 1. So which means that and remember these is supposed to be the left-hand side for the n plus 1, because you could write this back as this. So when we work this one out, we found that we end up with the correct formula. All right, well, this took much longer time than what I thought it will. But anyway, so this is all the material on chapter 1. All right, so we stop writing.